welcome to the Explainer. So, if you've spent any time tinkering with large language models, you know they can honestly seem like magic. Right up until they confidently spit out a completely illogical, wildly incorrect answer. It's so frustrating. Today, we're diving into a highly advanced prompt engineering technique called self-verification prompting. This is literally designed to fix one of the most annoying flaws in AI reasoning. Basically, we're going to look at how to get an AI to double-check its own homework.
To get the solution, we kind of need to understand the problem first. Imagine an AI trying to solve a really complex multi-step math problem. What actually happens if it makes a tiny, seemingly insignificant calculation mistake right on step one? Well, because these AI models generate text sequentially, that one early mistake acts just like a domino. It knocks over step 2, which knocks over step 3, and boom, before you know it, the final answer is completely derailed.
Now, you might be thinking, wait a minute, doesn't chain of thought prompting fix this? And yeah, standard chain of thought is great. It forces the AI to show its work and simulate human thinking, but it has a massive flaw, cascading errors with zero self-correction. If an AI hallucinates in step 1 of a chain of thought prompt, it doesn't stop and say, whoa, actually, scratch that doesn't make sense. No, it just confidently carries that wrong number all the way to the very end.
So here's our roadmap for this explainer. We'll start with the chain of thought problem, then introduce the self-verification solution. After that, we'll break it down into step 1, forward reasoning, and step 2, backward verification. Finally, we'll look at the real-world results and limitations.
Part 1. The chain of thought problem.
Historically, fixing this domino effect required training an entirely separate, super expensive verifier AI model just to check the math of the first model. But as you can imagine, that requires a massive amount of human-labeled data and a ton of expensive compute. It's just incredibly inefficient. But researchers realized there was a much simpler, cheaper way. To find it, they asked a really basic question. How do humans check their math homework? Think back to your high school algebra days. If you solved an equation and got x equals 5, how did you know for sure if you were right? You verified it, right? You plugged that 5 back into the original equation. If the math checked out, you knew your conclusion was totally correct.
Part 2. The self-verification solution.
So what if we could get large language models to do exactly that? What if models could plug their own conclusions back into the prompt? That is the entire essence of self-verification prompting. Evaluating the correctness of a generated response by using it to predict the conditions in the original context. The absolute crucial point here is this. If the original condition given in your prompt can be successfully derived from the AI's final conclusion, then the AI's answer absolutely must be correct.
Implementing this is actually a pretty straightforward two-stage process. Step 1 is forward reasoning, where the AI comes up with some possible answers. And step 2 is backward verification, where the AI checks its own work to see which of those answers is the right one. Let's break down exactly how you execute both of these.
Part 3. Step 1. Forward reasoning.
In a standard prompt, you just ask the AI a question and you get one answer back. But for self-verification, we need options. We want the LLM to generate multiple candidate answers to a single problem, using chain of thought prompting. To get these different options, we use something called sampling decoding. Think of it like turning a dial on the AI's creativity. By tweaking back-end settings like temperature or top K, we basically force the AI to generate slightly different reasoning paths and, as a result, give us different candidate answers to test. Let's look at a concrete example from the source material. The prompt is super simple. Jackie has 10 apples. Adam has 8 apples. How many more apples does Jackie have than Adam? Okay, let's say our AI generates 2 candidate answers. On the left, candidate A1 hallucinates entirely. It says Jackie has 10 plus 8 equals 18 more apples. So obviously this AI is struggling with basic subtraction. On the right, candidate A2 hits the nail on the head. 10 minus 8 equals 2 more apples. Okay, we have our candidates. Now how does the AI figure out which one is right without us stepping in to tell it?
Part 4. Step 2. Backward verification.
This is where the magic happens. We prompt the AI to act as its own teacher and grade those candidate answers using 3 progressive steps: rewrite to declarative, mask a condition, and verify. Let's walk through these. For the very first substep, we use a prompt template to force the AI to rewrite the original question along with its candidate answers into flat, complete declarative sentences. We literally strip away the question marks entirely.
This leaves us with pure statements that combine the original facts with the AI's generated conclusions. So A1 says Jackie has 18 more apples. A2 says Jackie has 2 more apples.
Next up is the masking step. We take those declarative sentences and we hide one of the original conditions from the prompt. In this case, we hide the fact that Jackie started with 10 apples, and we replace it with X. Then we turn the whole thing back into a question for the LLM. It becomes, Jackie has X apples, Adam has 8 apples, Jackie has 2 more apples than Adam, what is the value of X? Finally, we pass these newly masked questions back to the LLM. Now think about this. If the AI tries to solve for X using the bad logic of candidate A1, it will completely fail to get back to the original 10 apples. But if it uses candidate A2's logic, where Jackie has 2 more apples than Adam's 8, it perfectly calculates that X equals 10. So, we repeat this process multiple times, let's say 5 times, and we tally up the correct predictions. Whichever candidate logic successfully predicts the masked variable the most often, that one is crowned the final verified correct answer.
Part 5. Results and Limitations. So this is a brilliant theoretical framework, right? But does it actually work in the real world when dealing with complex reasoning tasks? The answer is a resounding yes. When researchers tested self-verification prompting, it achieved brand new state-of-the-art performance in 6 out of the 8 reasoning datasets tested. It dramatically outperformed older methods, proving that, yeah, AI is highly capable of checking its own logic if you structure the prompt correctly.
And here's a stat I find really fascinating. 2.33%. Now, you might assume this technique is only useful for older, less intelligent models. But researchers found that even for highly advanced models like InstructGPT, this technique still drove an average accuracy improvement of 2.33%. Now, that might sound like a tiny drop in the bucket, but at the absolute cutting edge of AI, squeezing out even a single percentage point of improvement on advanced models is incredibly difficult. It proves that even the smartest models out there benefit from double-checking their work.
However, we do have to be objective about the limitations here. First, this whole process entirely relies on the model's baseline ability to generate at least one correct candidate answer during that initial forward reasoning phase. Because of this, it's really not ideal for smaller, less capable language models that might honestly never guess the right answer. And secondly, generating multiple candidate inference chains drastically increases your computational cost. You're basically asking the model to do a lot more heavy lifting just for a single final output.
Which leaves us with a really critical question to ponder as we wrap up this explainer. Is the cost of extra computing power worth the guarantee of a correct answer? I mean, if you're building a simple customer service chatbot, probably not. But what if you're using AI to diagnose a patient, model global markets, or write critical software? How much is absolute certainty worth to you then? It's a massive trade-off, and honestly, it's one that will absolutely define the next generation of AI development. Thanks so much for joining this explainer, and we'll see you next time.